Okay, this is the lesson for the first part of 1.4. 1.4 is about function operations and function composition, or building functions from functions, they say. So we're going to start here with f of x equals to x squared, g of x equals square root of x plus 1. So my first one I'm going to do is f plus g of x. Hopefully you'll like these. These ones are pretty easy. F of x is x squared, which, what does this really mean? It means f of x plus g of x, which is simply f of x is x squared, g of x is square root of x plus 1. I'm going to put the g of x in red here. And I look and I see, can I simplify this? No, I can't add anything in a square root to an x squared. I'm done. That was all there is to function addition. Function subtraction, same thing, except I put a minus sign in the middle. Minus g of x equals x squared minus square root of x plus 1. Let's do that in red again. Okay. Oh, I forgot to talk about the domain of this. The domain. X squared can be all real numbers. However, the square root of x plus 1 is simply, can only have square roots of positive numbers. -1 is what makes this inside 0. And positives like for 0 and other positives will keep it positive inside the square root. Inside there has to be positive. So the domain is -1 to infinity. My next one, same thing. My third one is going to be fg of x, or sometimes thought of as f times g of x. So this is f of x, and now I'm just going to multiply it by g of x, which in this case gives me x squared times square root of x plus 1. Make sure that anytime you have multiples, and we'll deal with some of these later, you plug it in. And you plug it in with parentheses. This one, the square root takes care of my parentheses. But you plug it in with parentheses, and then oh, I forgot to do red. And then when you plug it in with parentheses, you FOIL if needed. Again, nothing's changed about this. X squared can still be all real numbers, but multiplied by something that can only be -1 to infinity, so that's my domain. This one will have a slightly different domain, f over g. I've still got my restriction, that's f of x divided by g of x. I've still got my restriction for the square root part, which is the -1 to infinity. But I also cannot have it equal to 0. And so the square root has to be larger than 0. This one no longer includes the -1 here, like the 3 above it did with the bracket. It is just strictly -1 larger than -1. The last one they show us is g times g. What does that mean? It means g of x times g of x. Could also be thought of as g of x squared. This is where domain gets a little tricky. Square root of something squared is x plus 1. The problem is with my domain, x plus 1 would be a domain of all real numbers, or negative infinity to infinity. But my original function g didn't allow for that. I usually look at it in this step or this step. I need to look at it before I simplify out the square root. My domain is still negative 1 to infinity, because I could not put something more than that into my original thing, this g, or looking at it in this step, this g, or for that matter, that g. Okay. You cannot take more than what was originally able to be put in. Example 2 here, now we're going to talk about function composition. And we're going to be looking at f of g of x. This means functionally that g goes into f of x, or my input becomes g of x. G of x I know is square root of x, so that means I'm putting square root of x into my x and g of x. So g of x, or f of x, sorry, square root of x into my x and f of x. G of x is square root of x, f of x is e to the x, so I'm replacing the x in e to the x with square root of x. So here I have e to the square root of x. If I want to talk about its domain, again, I can only plug positive numbers into the square root, so its domain is 0 to infinity. E can be taken to anything, but it can only get positive numbers. Its graph looks kind of like domain only has the positive numbers. Looks kind of like that. My second version of this, if I turn the functions around, I end up with something different. G of f of x means I'm going to now plug, I go inside to out. So f was on the inside, so f goes into g of x. And this does produce a different function. And we'll look at the graph too. Again, if you're not sure about what these graphs look like, you can graph them on your calculator. And we'll take a look, and I'll put them into the calculator in a second. So this equals g of f of x here is e to the x. So that means e to the x is going into my x and square root of x, which is going to be square root of e to the x. Now, e to the x has a range that's always a positive number. So e to the x will always be a positive number. This one ends up with a domain that's negative infinity to infinity, because e to the x takes negative values of x and outputs them as a small but positive value of y. And its graph looks like about like that. Okay. Let's take a look at this on the graphing calculator. I'm going to graph the original functions and the composed functions. So I'm going to start with square root of x. I will then go to e to the x. So square root of x is blue, e to the x is red. I'm not actually mixed. Now let's do this. We'll match the colors in the book. Square root of x is going to be purple. And e to the x is second function of that ln button. Right. If I want to delete just a single one, there's this delete button, kind of a little over from second. And that can work for me. Come up here. This is e to the square root of x, was the blue one in the book. And the calculator kind of default types over itself. I want to get back to a standard zoom, so I'm going to do zoom 6. So our original was the black one, square root of x, and the purple one. And depending on the order we combine it in, square root of e to the x just looks like e to the x, but it grows slower. E to the square root of x looks kind of more like a combination. It's kind of like the square root. It's starting to curve up. Square root grows slowly, but the exponential power grows faster. I think we'd see that more if I took my y's. I'm going to change my window, make that 50. And I don't like scales of 1, so I'm going to make it 5. I don't like scales of 1, they get too cramped together. Here, I'll show you what the scale of 1 is, and then I'll show you the difference. See, this is very cramped together. Yes, the square root of x1, e to the square root of x, that's a, is growing kind of quickly. It's starting to look more exponential. My blue one, blue, e to the square root of x is starting to look exponential as I go on. I don't like how many lines there are. So when I talk about changing the scale on the window, if I change my Y scale to 5, this one wasn't too terrible. They're a little less cramped together and I can see all of them. Last thing we're going to talk about is finding a little bit more complicated domains and ranges of function compositions. So for that, we're going to use example 3. And we're going to do f of g of x and g of f of x. So f of g of x, remember that that is f of plugging g of x in for f of x, which can be thought of as f of, since g of x is square root of x, that's what's getting plugged in. No, I don't need the f anymore. X is square root of x. I do usually plug it in parentheses. That gets squared and then has 1 subtracted. Square root of x squared is x minus 1. When I'm looking to analyze domain, I want to use this unsimplified version because that's what I plug into originally. It has to go through G first. So if it's not in the domain of G, it can't be in the domain of the final. It also, what goes through that domain has to be acceptable to the domain of F. Again, the easiest way to do that is deal with this unsimplified version and look for its domain. I've got a square root. I can't have the square root of a negative number, but I can include 0, so its domain goes 0 to infinity. The answer should not look like the unsimplified version. The answer should look like x minus 1, but I need that unsimplified version for the domain. To turn it around and do g of f of x, we'll do that same thing with the domain. G of f of x is g of, nope, wrong color. G of f of x and that equals g of f of x being x squared minus 1 that is square root of x squared minus 1. Now this one's a little bit more complicated domain. I cannot have the square root of a negative number. Well, if x is like 2, that's 4 minus 1, that's fine, that's 3. But if x is 1/2, 1/2 squared is 1/4. 1/4 minus 1 is a negative number. I can't do that. And in fact, I can't do that for any value that's smaller than 1. So I have 1 to infinity. But squaring negative numbers makes it positive. So negative 2 squared is 4 minus 1 is 3. Something like this. That's square root of 4 minus 1. Square root of 3, that's fine. Again, it can go, all the negatives are fine until I get past negative 1, where my squares are less than 1. So my domain here is negative infinity to negative 1. Actually, I did these backwards of what the book does, but that's okay. Okay. This one does not have a simplified version. But again, when I'm doing domain, I always look at the unsimplified version. Okay. The graph of this one, if you enter it in the unsimplified version into your calculator, it will work. It is just x minus 1, but only keeping the positives. Again, closed circle because I included. This one, I would probably want to look at on the calculator. It looks like this. I'd enter it into my graphing calculator. I'm going to show my closed circles at negative 1 and 1. That is it for the first half of 1.3.